Someone asked a good question after the lecture. I had made this claim that when you have a decision tree, and you expand out each path into a monomial. Let's do it this way. Take the sum over all of these monomials, that you get a sparse polynomial. In particular, I said that if the decision tree has t leaves, this implied a t-sparse polynomial computing the decision tree. This isn't quite correct. What I should have done was introduced the following notation. If you have a function f I should have defined L1 of f to be the sum of the absolute value of the coefficients of the polynomial computing f. And there are two easy facts to see about this, about taking this sum of absolute values. One is that L1 of f times g is at most L1 of f times L1 of g. L1 of f plus g is at most L1 of f plus L1 of g. And then what is true is that a decision tree f with t leaves has L1 of f at most t, even though when you expand out this particular polynomial, when you start expanding out, you can imagine expanding out a product of 1 minus xi, you're going to get many terms. But the one norm of this particular function, it's not difficult to see, will be bounded by at most t. This is because each one of these has one norm at most 1. When you're taking a product, a monomial is going to have L1 norm at most 1. And then you're taking a sum, and so you're going to get L1 norm at most t. And then what you can say is that it's also an easy fact that there exists g, a polynomial, such that g is L1 of f over L1 of f squared over epsilon sparse, and the expectation of g minus f squared is at most epsilon. So you give me a function whose L1 norm is bounded. There exists a function g that is sparse in this sense and closely approximates f in L2. And g is simply f where you zero out all of the coefficients of the polynomial that have magnitude less than epsilon over L1. It's not difficult to see. So I was being sloppy, and I was interchanging the notion of bounded L1 norm and sparsity. But for the purposes of learning, with respect to the uniform distribution, they're in some sense equivalent. OK, so that's one correction I wanted to make. Another thing I should have mentioned, this is regarding, or I wanted to mention Mansour's conjecture. I'll just remind you, this is the conjecture that for any DNF formula with S terms, there exists a polynomial P such that expectation of f minus p squared most epsilon, and let's just say the one norm of P is at most s to the order log 1 over epsilon. What I should have said, I mean, this is the correct conjecture. What I wanted to say is that it's known, and Mansour proved this himself, that you can construct a P. So there exists a P such that the one norm of P is at most S to the log S times log 1 over epsilon. So, you know, we're pretty close to solving. I mean, you know, it's not too far off. And another thing I wanted to say, although I won't get into this at all, is that Mansour's conjecture is implied by the entropy influence conjecture. And since I don't want to get into what the entropy influence conjecture is, if you're familiar with the notion of the entropy of a Boolean function and the total influence of a Boolean function, the conjecture is simply that the entropy of a Boolean function is always less than or equal to some constant times its total influence. And it turns out that if this conjecture is true, Mansour's conjecture is an easy consequence. You know, if you can find a counterexample to Mansour's conjecture, you'll disprove the entropy influence conjecture. So it's still, and there are also some learning applications that we'll be able to talk about after I talk about learning with noise some more today. OK, so these are the two things I wanted to mention. And then someone else suggested that if the viewers at home want to email me a question, I will take a break in about an hour and check my email. You can email me at klivans@gmail.com. I'll check my email, and if I have any interesting questions, or if I have any questions at all, I will mention them about an hour into the lecture. We'll take a very, very small break.
Can we also email you?
Yes, absolutely. Although I know your emails will not be of a technical nature. OK.
Can I ask you two questions about these two problems?
Yes.
You said something about you were not too specific, that this conjecture is known to be true for, you said some random.
Oh, yeah. OK, so I wrote a paper with Homin Lee and Andrew Wan. Andrew is here, I think. Well, maybe not. Are you here, Andrew? No, he was here yesterday. And what we prove, there is sort of a cute proof that if the DNF formula is read once, so each variable literally appears once, then the entropy influence, or then the Mansour's conjecture is true. If you do more work, you can improve this to read k for k constant. And you know, what we also prove is that if you choose a DNF formula at random, and we consider several different models of choosing a DNF formula at random. Pick any kind of natural way you would choose a DNF formula at random. The Mansour's conjecture is going to be true. Do you want me to briefly mention why this is true, or?
If you think it's worthwhile.
I can do it in 2 minutes. So I can give you a feel for why it's true. So maybe this is slightly interesting. So imagine you had a DNF formula. Let me give you a very specific DNF formula. So x1 and x2 and x log n, or x log n plus 1, log n, or, OK, so I'll have, let's say n terms, each of length log n.
Roughly the tribes.
Roughly the tribes, yeah. OK. So, so the probability that any one term, say the fixed term, is satisfied, is 1 over n. And in expectation, so the expected number of terms satisfied is 1. And furthermore, the probability that more than, say, log 1 over epsilon terms, the probability that any one of these is satisfied is 1 over n. I have n terms. So
not n over log n.
Not n over log n. I'm doing
n log n.
Yeah, n log n variables.
Okay.
Yeah. The probability that more than log of 1 over epsilon terms is satisfied is at most epsilon. OK, now, so consider the following just univariate polynomial. At 0, it will be 0. And then I'm going to interpolate it so that at all of these discrete values up to log 1 over epsilon, the polynomial is exactly 1. OK? And then, so I don't know what the polynomial is going to do after you go beyond log 1 over epsilon. It's probably going to increase dramatically. And I'm not interested in what it does over here. But I do want to assure that there's some polynomial, let's say g, that interpolates um, 0, 1 to log 1 over epsilon appropriately. And then I'm going to consider the following polynomial, that is just g of t1. I'm going to view t1 as a monomial. I'm just going to multiply all of the variables together. G of t1 plus tn. And so what, when this sum is 0, g is going to be 0, because we interpolated that particular value. When this sum is between 1 and log 1 over epsilon, g is going to be exactly 1. So it completely agrees with this polynomial whenever the sum is between 0 and log 1 over epsilon. And then g may err when this sum is greater than log 1 over epsilon. But the point is that that happens with low probability. So you can just compute that the expectation of g minus f squared is at most epsilon, or it's going to be some function of epsilon. You can choose epsilon appropriately. And also, the degree of g is log 1 over epsilon, because it's roughly log 1 over epsilon, because we only interpolated about log 1 over epsilon values. So when you expand out this polynomial, it's not difficult to see that it satisfies the conditions from n-source conjecture. Okay. So this is the simple idea. Maybe the most interesting thing about it is that it does not, you can prove that man-source conjecture is true for this DNF without doing sort of the more standard kind of Fourier tricks on the Boolean function. It's more just a question about polynomial interpolation. And then if you'd like to recapture these other results, read k, and also if the DNF formula is random, you need to prove some sort of concentration that with high probability not too many terms of a DNF of that form are satisfied. And it's not too difficult to do for the random case. It's, for some reason, it was very tricky for the read k case. But that's the main idea. Let's see. So let me summarize what we discussed last time. We considered the following optimization problem. We wanted to minimize over, so we fixed a Boolean function. and we wanted to minimize over all p such that L1 of p is at most t, we wanted to approximately minimize the expectation of p minus f squared. And we saw that we could do this. The learner needs queries. To f. And this was a result of Kushilevitz and Mensor. OK, so another interesting optimization problem that you might consider, instead of putting this constraint on the polynomial, would be that you want to minimize over all polynomials such that the degree of the polynomial is at most d, expectation of p minus f squared. Okay, so here we're trying to minimize with respect to sparse polynomials. Here we want to minimize with respect to low degree polynomials. And this is there's a simple algorithm for doing this. This is the low degree algorithm of Linio, Mensor, and Nissan. And the learner will not need query access to f. So again, we can assume that there's some fixed function f. Instead, the learner can just receive x, f of x, passively randomly chosen examples. On the other hand, whereas this was a polynomial time algorithm in all of the parameters, polynomial in 1 over epsilon and t and n, this algorithm will be polynomial in n to the d and 1 over epsilon. Okay, so they're just incomparable setups. In the case when we were optimizing, when we were trying to find the best fitting sparse polynomial, it was clear that what you should do is take the largest Fourier coefficients, the largest coefficients of the polynomial. In this case, again, because we have the Plancherel equality or Parsifal's equation, we know that the correct thing to do is take all degree d or less of f's coefficients. And by that, I mean when viewed as a polynomial. OK, so remember, we know that f can be written as some polynomial. The coefficients are these f hat of s's. And if you want to find the best degree d polynomial that approximately minimizes, this quantity, the correct thing to do is to output p, which is equal to the sum where the size of s, the size where is at most d. So we're only taking the degree d and less coefficients. I'm just claiming that it's easy to see that this is the best fitting degree d polynomial because of Parsifal's equation. Now remember, we need to actually output. We know this is the correct polynomial. How do we find it? In this case, when the polynomial was sparse, we had to do this searching over prefixes of coefficients. Here, the algorithm is simpler. We will enumerate, so the algorithm, we will enumerate all monomials chi-s with s less than d and estimate f hat of s. And remember that f hat of s equals the expectation of f of x times chi s of x. Okay, so given random examples, we don't need query access to f anymore. Given random examples, x from -1, 1 to the n, I can, I'll take my random examples and labels, and I'll see, approximately what is the correlation of my function with this particular monomial chi s. That will give me a good additive estimate of what f hat of s is, and then I'll just output the sign maybe I'll call these, this is the estimated f hat of s. And this will be my output hypothesis. If you've seen this before, I mean, as always, bear with me. There's a reason why I'm sort of spelling it out this way. Okay, and then one of the, I guess the next question is, what sort of functions can you learn using this type of low degree algorithm? So what functions are learnable? Using this algorithm? Well, to that end, we say that a function f is epsilon d concentrated if the sum of all the coefficients on levels above d, the sum of their squares, is at most epsilon. Okay, so if a function is epsilon d concentrated, it means that the mass of its spectrum above level d is at most epsilon. And therefore, it suffices to estimate all of the Fourier coefficients that lie, all of the coefficients on monomials of size d or less. So it's easy to see that these functions, well, just by definition, these functions are exactly the ones that are learnable by this type of algorithm. And then the next question is, so another interesting, well, a very interesting and fruitful framework has been to find or prove that classes of functions, or hopefully as large as you can, classes of Boolean functions are concentrated and the main result of LMN is that if f is a size s depth d circuit, okay, so this certainly encompasses decision trees. DNF formulas would be depth 2. Then f is epsilon order log s over epsilon to the d minus 1 times log 1 over epsilon concentrated. And Johann actually improved this exponent to d minus 2. And this immediately implies, a quasi-polynomial time algorithm for constant depth polynomial size circuits. Also known as AC0. And the main technical tool, which I will not at all get into, is a very beautiful relationship between the effect that a random restriction has on a circuit and its ability to be concentrated as a Fourier polynomial. And so it's not surprising that Hofstede's switching lemma is at the center of it all here in this result. So I just wanted to mention this particular application. I'm not going to get into the proof there. OK. So what I would like to do now is show you how to learn juntas, because we've sort of developed the technology. And just recall that a junta is a function minus 1, 1 is a Boolean function that depends on only k inputs, k variables. Okay, so one way to think about a junta, or a k junta, is that it's a polynomial whose Fourier polynomial, so the Fourier polynomial for this junta has at most 2 to the k non-zero coefficients. Any coefficient that involves a variable that's not relevant to the function will be zeroed out. And each coefficient has magnitude at least 1 over 2 to the k. So, we've talked about finding polynomials, the large coefficients for polynomials, or estimating their coefficients. Here, the difficulty is that you're given random access to this junta that only depends on k inputs. So you can think of it as a polynomial with 2 to the k non-zero coefficients. And you're just trying to find, the goal is to just find some non-zero coefficient that's hidden amongst all of these, potentially. I mean, you may need to, naively, you could try all 2 to the n coefficients and see if any of them is non-zero. There are, 2 to the k of them sitting there that you need to find.
Sorry, each coefficient has magnitude?
Yeah, every coefficient has magnitude at least 1 over 2 to the k. Every non-zero coefficient has magnitude at least 1 over 2 to the k. I mean, so.
Oh, just because of the big thing is.
Yeah. I mean, there's it's like a granularity issue here.
Yeah.
Okay, so the naive algorithm, so just take my word for it that this problem, the learning juntas problem, does indeed reduce to finding some non-zero coefficient of this polynomial that computes the k junta. And so the naive way of solving this problem would be to just enumerate over all degree k or less monomials and estimate its coefficient. And this algorithm will take time roughly order n to the k to enumerate over all monomials of degree k or less, times 2 to the k. I may need to use this many samples to estimate. I mean, if it's as small as 1 over 2 to the k, I'm going to need roughly 2 to the k samples just to see that it's non-zero. And let me remind you that we do not, there's no query access to f. It's easy to see that if you have query access to f, you can learn juntas in polynomial time. OK, so as I mentioned last time, Mossel, O'Donnell, and Servideo gave an n to the 3/4 k time algorithm. This is actually omega over omega plus 1. Yep.
Sorry, it doesn't make sense to me to write 2 to the k when you ignore the k factorial in the denominator.
What k factorial in the denominator?
It's n choose k.
Okay, I mean, would it make you feel better if, no. Wait, what's the problem here? It's at most, yeah, it's n choose k, which is at most n to the k.
Yeah,
I mean,
no, but if you're considering factors depend only on k, there is a k factorial in the domain. It's n choose k, it's not n to the k.
Making an overestimate.
No, that's fine. No. I'm not saying that this is incorrect. I'm just finding it strange because.
Oh, you're saying I'm overestimating here.
There is a k factorial in
sure,
the denominator.
right, but
so why do you even mention the 2 to the k?
Oh, yes.
You
okay.
threw away k factorial, but
okay, because, yeah, I did this because, you'll see in a second why I did this. Okay, I just wanted to point out, okay, you're right, and what I wanted to point out is that, that in order to, the sample complexity for every coefficient is at most 2 to the k. Okay. That will come into play in a second. So good. So let me show you this result. And as I said, there's an improvement by Greg Valiant that uses this as a subroutine and improves upon it to get to like n to the 0.68k or something like that. Okay, so I need, in order to show you this result, which is actually very simple, I need to make a small digression and talk about learning GF2 polynomials. So this whole time we've been representing functions as real polynomials. It's also true that every f, and now I'll write it as 0, 1 to the n, to 0, 1, can be written as a GF2 polynomial of degree n, at most n. So this is an easy fact. You can just interpolate all 2 to the n values using an appropriate monomial. So, you know, when we were talking about Fourier polynomials, and we had these monomials of degree n, the product of all the variables. So when we're working with respect to GF2 polynomials, of course, this becomes x1 plus x2 plus xn. So here's a question for you. So you have an unknown parity function. So it's sum of some, it's some mod 2 of some subset of these variables. I'll call it f. And you want to learn what f is, given random examples labeled by f. Okay, so, you know, the unknown parity could be x1, xor, x4, xor, x6, xor, x7. You know, you don't know what it is, but what you're given are random examples labeled according to some unknown parity function. And you're asked to figure out what the unknown parity is. And it's, so for someone who hasn't seen this before, do you know what the algorithm is to figure out what the unknown parity function is? Okay, yeah, I guess Johan sort of mentioned it yesterday. I can view, you know, I can view each one of these as a linear equation mod 2. Okay, so this corresponds to a2 plus a4 plus a5 equals 1. This is all mod 2. And these AIs are kind of the coefficients of the variables in the parity. This one is A1 plus A3 plus A6 equals 0, and so on and so forth. And I know that there is a solution to this system. So this induces a system of linear equations mod 2, and I can find a solution. So I can find a solution to the system of equations, and that solution will be consistent with all of the random examples that I've seen. So this. Okay, and if you remember from last time, if you take a large enough set of random examples and you can find a solution or some hypothesis, in this case a solution to the system of equations that's consistent with all of these random examples, then it's easy to prove that this hypothesis will generalize well. And so this really is the correct, this really will be an accurate hypothesis. Okay, so it's so it's well known and it's easy to find to learn an unknown parity function. And now I want to consider the following generalization. So let f be a degree d GF2 polynomial. In this case, the degree of f was 1. But here I have f. It's a degree d GF2 polynomial. The claim is that f can be learned in time roughly order n to the 3d. And this is a simple trick that I'll refer to as feature expansion. So if f is a degree d GF2 polynomial, then it has at most n to the d terms. And so I can write it as a sum of n to the d new variables where I have a new variable for each unknown coefficient of f. So just like in the degree d equals 1 case, I had n coefficients corresponding to the unknown coefficients of the unknown linear polynomial over GF2 that I was searching for. If I have a degree d GF2 polynomial, then it has at most n to the d terms. And I can come up with a set of n to the d new variables. Each one corresponds to one of these unknown coefficients. And the nice thing is that then this reduces to learning parity over n to the d variables. And certainly I can solve a system of n to the d linear equations in n to the d variables in time n to the 3d.
So this is relinearization?
I call it feature expansion for because when hopefully we'll get to kernel methods, you're kind of introducing a new feature. Yeah, I guess you could call it. I think it maybe in some circles is referred to linearization, but you know, each one of these new coefficients I consider a feature of the original space. Okay. Good. So the last thing we'll need for learning juntas is this result due to Siegenthaler.
I have a short question.
Yes.
So is there a small fact that you swept under the rug that in the first case with parity, this matrix is building up, we perfectly understand it and thus can analyze. In here it is a little bit more difficult, and therefore it's into the 3D and not into the D.
Oh no, I'm just saying that, you know, this could be like, you know, using faster matrix I mean, there's some complexity here for solving a system of linear equations.
Oh, but the number of samples is still something like into the D?
Yes. Yes. So the point is, right, so there is sort of something on, you know, the number of samples you need to kind of get an accurate hypothesis before you generalize. In order to get generalization power of your hypothesis for a parity, you need, you know, at least n examples. In order to get kind of generalization power for a degree D polynomial, you can imagine it's going to be larger.
I mean,
how much larger is it? It's exactly n to the d.
I want the matrix to be full rank, right?
It doesn't. No, it doesn't matter.
What?
It doesn't matter. You can output any solution that's consistent with your system of equations.
Oh, that's the definition of the task.
Well, that's in order to learn. If you may, so recall from last time, I said all you need to do in order to learn is take a sufficiently large set of examples and find a consistent hypothesis with that set of examples. So take a sufficiently large system of equations, output any consistent solution, it will generalize. There's a difference between, like, you know, exactly solving a system of linear equations and learning. There's a subtle difference.
But in parity, isn't it like either I learn it perfectly or I output a parity that's uncorrelated?
For the uniform distribution, yes, but this could be an arbitrary distribution.
Ah, okay.
Good question. Okay, so the last fact we'll need, which was rediscovered, I mean, it was discovered by Maslow, O'Donnell, and Servideo, and they discovered later that it was already known, so they reproved it. It's a cute result. It basically says if f is such that f hat of s is equal to 0 for all s less than or equal to d, then the degree of f as a GF2 polynomial is at most n minus d. Okay, so you can sort of see already that we're in good shape here. You know, remember, you're searching for just one non-zero Fourier coefficient. And what this structural theorem says is that, well, if all of the low-order Fourier coefficients are 0, then it's actually computed exactly by a low-degree GF2 polynomial. So
f could be the parity function.
f could be the parity function.
That's an example where d equals n minus 1.
Yep.
Sorry?
If it's the parity function, all of its low-order coefficients are 0. All n minus 1 of degree n minus 1 or less are 0. But it is a degree n. It's a degree 1 GF2 polynomial, n minus d.
It's still on the board.
Yeah. Right. D is n minus 1 in that case.
Sorry, I'm confused. So the degree is.
If it's a parity function, then it's Fourier polynomial viewed as a real polynomial is 0 for all s less than or equal to n minus 1.
Right.
So then this becomes, so it's a degree n minus 1. It's a degree 1 GF2 polynomial. Okay. So to see this, I mean, the first thing, so there's one fact that the degree of f as a GF2 polynomial is always less than or equal to the degree of f as a Fourier polynomial. So let f be such that f hat of s equals 0 for all s less than or equal to d. And then consider g, which is equal to the parity on all. So I want to take the parity on all n bits times f. And then g so
just complement it.
Yeah, so right, that's what I'm trying to do. So g is the complement of f. So g hat of s is going to be 0 for all s greater than n minus d. So the GF2, right, so the GF2 degree of G is going to be at most D. But notice that
N minus D. No?
Yeah, you're right. Sorry. But notice that the GF2 degree of G equals the GF2 degree of F, because in the GF2 scenario, I can write G as x1 plus xn plus F, and I haven't increased the degree of G at all. So the GF2 degree of G is n minus D. It turns out they're equal. So the GF2 degree of F is at most n minus D. Just yeah, as Nati said, it's a simple complementation.
How difficult is this fact?
Which fact?
Oh,
this one?
That's where you wrote fact.
It's simple. I mean, you can really just look at the interpolating polynomial for F and just mod out its coefficients. Or sorry, you can take an interpolating polynomial, a Fourier polynomial, and mod out its coefficients, and that will get you a GF2 polynomial. You can write F's Fourier polynomial such that all of the coefficients are integers, and then you can mod out everything by 2.
So you sort of make a linear transformation, so the basis is 0, 1 instead of minus 1, 1. You get these powers of 2 disappears.
Exactly. Instead of using minus 1, 1, you use 0, 1. You'll get integer coefficients, and you can mod everything out. Yeah. Just like when we were doing decision trees, and I was writing things as 1 minus x1 times 1 minus x2 times 1 minus x3 plus something else. I mean, you can do that for an arbitrary function. Expand everything out. You'll get all integer coefficients. Okay, so now what we're going to do is choose D to be 3k over 4. So either we run the low degree algorithm in time n to the 3k over 4 times 2 to the k to sample each coefficient, which is why I was saying, I mean, if you don't have the 2 to the k, if you have n to the 3k over 4, then you get n to the 6k over 8, and then that destroys their bound. So, so either you run the low degree algorithm in this time, or you learn it as a GF2 polynomial, and again, we'll have n. Remember, it was a k junta, so it'll be k minus d. So we'll choose d to be 3k over 4. So you'll get, but remember, you have a 3 here because you have to solve a system of equations. So this is low degree algorithm, and n to the 3k over 4. This is a GF2 polynomial. So either you run this algorithm and you find some non-zero coefficient that gives you a relevant variable and you move on, or you learn it as a GF2 polynomial. OK, any questions on that? Or?
And you can replace 3/4 by omega over omega. You
can replace 3/4 by omega over omega plus 1. And as I said, Greg Valiant has an improvement to that even. So not to take anything away from this result, it's very nice. On the other hand, it's very, very simple. You would think that certainly this shouldn't be the right bound. There should be something kind of more sophisticated that we can do. I think that Avram Blum will give you $500 if you can do time order n to the k over 2. This is still open. It might be $100, but now I guess it's $500. I can't remember. He wrote it down somewhere. You can look it up. OK, so now I want to finally start moving on to learning with noise. Oh, maybe this is a good time to check my email. See if anyone wrote me something. Let's see. I have to get out of airplane mode. Nope, no emails, so we can move on. Thank you. All right. So remember this, I don't know why I erased this, but these are the two sort of optimization problems that we know how to approximately minimize. This one needs queries, F. This one just needs random examples. Good. So I want to talk about something called agnostic learning. And you'll see why it's a noisy model of learning in just a second. So I want to fix an arbitrary Boolean function. And the analogy here is, remember when we were learning decision trees, f was some unknown decision tree. Here, f is totally arbitrary. And then I'm going to define a quantity opt, which is going to be the minimum. OK, so I also want to fix some concept class, C. Here you can think of C as being decision trees if you'd like. Now I want to define a quantity opt. It's the minimum over all C and C of the probability when x is chosen from -1, 1 to the n, that f of x does not equal c of x. So this is the error rate of the best fitting concept C with respect to F. Okay, and then the goal of the learner is to output H such that the probability that H of x does not equal F of x is at most opt plus epsilon. And you would like to run in time polynomial in n 1 over epsilon.
Does H have to come from C?
No. No. That would be proper agnostic learning, but no, I'm not going to make that restriction. So what's going on here? Well, imagine that you're given access, black box access to some function f. It's not computed by a decision tree, but there's a decision tree that agrees with 3/4 of its inputs. In that case, opt is 1/4, and it seems reasonable to ask the learner to output a hypothesis that has error at most 1/4 plus epsilon. Almost equivalently, well, in this setting equivalently, you can think of an adversary who comes, takes a decision tree, and adversarially corrupts 1/4 of its inputs, and then gives you black box access to this corrupted function. Another thing to notice is that I could take a decision tree and, my function f could be completely random on, say, an opt fraction of the inputs. And it would be unreasonable for me to expect to output a hypothesis that has error rate less than opt if that fraction of inputs is chosen totally randomly. Good. So in the case that another thing to notice is that opt equals 0 is the pack setting. This is the setting we've been working in yesterday and for the first half of today. If opt is 0, this means there actually is a concept in your class that agrees with F. Okay. And an even more general way to define this would be to fix a distribution D, a joint distribution, fix a class C, and to define opt to be the minimum over all C and C of the probability when x, y is chosen the D doesn't necessarily have to be uniform anymore. Okay, so there's. Oh, thanks. So here we fixed an actual function, and you thought of an adversary as corrupting some opt fraction of inputs. Here I'm just saying there doesn't even need to be a fixed function involved. It could just be any joint distribution D on your input space times the label space, and we can still define opt according to this definition. Also, there's no. I mean, this could have been. This could have been an arbitrary space. I mean, this could have been, for example, Rn. It didn't have to be the discrete cube, and later we'll be working over Rn. So I think it's a very clean formulation. It has a lot of nice advantages. You may be familiar with something called classification error. That's where, imagine you're given a decision tree and each label is independently corrupted with some probability eta. That is an easier model than this setting. And for various reasons, well, Well, for various reasons that we'll see very soon, this model has a lot of appealing features. It's typically attributed to, the definition is typically attributed to Kearns, Shapiri, and Selly from '93. Though actually David Hausler essentially defined this model. There was a very small twist that KSS had in '91. And this model, in a way, also goes back to the statistical learning theory work of Vapnik. It actually predates the PAC model. He was actually interested in, given a sequence of random examples, what is the best fitting classifier that you can find on this sequence of labeled random examples. Whereas sort of for Valiant's PAC model, you always assume that there's some concept that labels all of the points consistently. One nice thing about having an algorithm that works in the agnostic setting is that it's very robust. So you give me an arbitrary function, as long as there's some decision tree that is reasonably correlated with f, my learning algorithm is going to do something reasonable. In the PAC model, if you have an algorithm for learning a decision tree, and then you get say you see one example that's noisy, then all bets are off as to what your algorithm is going to do. It could just totally fail. So that's historically what happened. So now, what I want to talk about is an observation.
Can you tell me, I'm a little unclear on the quantification of the probability distribution. Is it like in PAC or?
Yeah, sorry. It's like in PAC. You should have an algorithm. If you have an algorithm that for, so first I guess you fix the concept class that you want to be competitive with. And then you should succeed. You should have an algorithm that succeeds with respect to every distribution. And I guess one thing that we'll be looking at is distribution-specific agnostic learning. And this will correspond to the case when the marginal distribution on, for example, -1, 1 to the n is uniform. For example, on -1, 1 to the n, this is the case when x is the hypercube. Or we could say d of x is Gaussian, or whatever other condition you'd like. And then that sort of corresponds to a case where you're getting these random examples. The location of the points of the randomly labeled examples are from some distribution that you're aware of. The label is completely adversarial. One annoying thing about agnostic learning is that it's difficult. For example, one of the simplest problems in PAC learning that I can think of is learning an unknown disjunction. Okay, so there's some unknown disjunction you're trying to learn. And you get a bunch of examples from some arbitrary distribution on, say, 0, 1 to the n, labeled positively if your disjunction labels it positively, and negative if your disjunction is false on this particular example. And then you're asked to come up, figure out what the disjunction is. It's easy to see how to learn a disjunction in the PAC model. Every time you have a negative example, and for any bit here that's 1, that means that literal cannot be in your disjunction, and so you can eliminate it from the disjunction. It's very simple to learn disjunctions with respect to arbitrary distributions on 0, 1 to the n. But agnostically, learning disjunctions seems much harder. So in the agnostically learning disjunction case, you're given these, where the marginal distribution could be anything, you're given these randomly labeled examples. You'd like to output the best fitting disjunction on these randomly labeled examples. We know how to solve this problem in time 2 to the square root of n log 1 over epsilon, I think. And that's the best algorithm. So we go from something like very, very simple to something quite difficult. You can show that this problem of agnostically learning a disjunction is actually harder than pack learning DNF formulas. So it's not surprising that we don't know how to beat the best bounds for learning DNF formulas. But yeah, so it's sort of a very difficult model of learning. Even these simple problems turn out to be quite tricky. And so that's why we're going to need to make assumptions on the distribution, the marginal distribution of the space. But we have to do something.
You know that the disjunction is small?
I mean, you can always do brute force search, but no. Yeah.
So to compare to the algorithms you have showed us before checking your email, in some of them we just estimated, for example, the Fourier coefficients by drawing random samples.
Right.
So if the optimum is small here, this should still work, right?
Okay, so that's what I was about to talk about. So that's a good question. So, so question one. Let's say F is epsilon d concentrated. Okay, so let's do this. So C is a class such that every C in C is epsilon d concentrated. Okay, good. So let's run, even though we're in, so let's assume that d of x is uniform over minus 1 to the n. Okay, so good. Let's just run, let's run the low degree algorithm. Let's see what happens. So, so now we have access to some distribution that's uniform on minus 1 to the n. It's a joint distribution on that times minus 1. And so let's try and minimize the expectation xy drawn from minus 1 to the n minus 1 of over all polynomials p of degree d of y minus p of x squared. Okay. And let's say that C, we'll say C corresponds to best fitting concept in C. Okay. So right. So this is going to be less than or equal to. So just to be concrete, I'm given a bunch of randomly labeled examples, and I'm going to run the low degree algorithm, and it will output some p of x. This is the best fitting polynomial in L2 that I can find given my sequence of random examples. Now this is going to be less than since my algorithm, finds the best fitting polynomial p, this quantity is, approximately. Let me just say this for a second. It's going to be certainly less than the error if you had outputted the actual Fourier polynomial of c hat. Okay, so here's a polynomial that you could have output. You're going to output the one that minimizes this quantity. This is going to be less than or equal to expectation over x and y of y minus c. I think I get a 2 here. Y minus c squared plus c minus squared. So I'm using the almost triangle inequality here. So I lose a factor of 2 because I'm adding and subtracting c and everything is squared. Now, this term here we know is, I think, 2 times epsilon. This is because we said that c is concentrated. And every time y, remember y is plus 1 minus 1, c is plus 1 minus 1. Every time they disagree, you're going to get a 2 in here, and then you're going to square that, you'll get a 4. So you'll end up with 8 times the probability over xy that c of x does not equal y. And this is opt. So you'll get 8 opt plus 2 times epsilon. Now, for whatever reason, and we made this observation, and we were working with Yishai Mansour, who's the M from LMN. He claimed that he was not aware of this. I don't know, that it has this sort of noise-tolerant property. You know, you would really like to, what you really want is opt plus epsilon with no constant out here. Why? Well, I mean, if you give me access to a function and say there's a decision tree that agrees with 3/4 of it, then opt is a quarter. This bound is meaningless. Its error is still 8 times a quarter and something greater than 1. Okay, so it's nice that it has some kind of weak agnostic property, but what you'd really like is opt plus epsilon. And you can also show that in the case when you would like to agnostically learn decision trees, you'd like to output the most competitive function here with decision trees. The same thing holds if you run the sparse algorithm. It has some weak agnostic, some weak noise tolerant properties. And you'll also get like 8 times opt plus epsilon, something like that. Okay. Now, we can fix this. So the way to fix this is instead of minimizing this quantity with a square, we should just minimize this quantity. And that's going to get rid of the squares.
And there's one more 2.
Oh, yeah. Hold on. I can't get rid of that. And this will end up with 2 opt. Don't worry, I can take care of this. But you'll end up with 2 opt plus 2 epsilon. And then if instead of outputting the sign of p of x, you output the sign of p of x minus theta, you can choose theta randomly. This is a little trick. Taking your polynomial p and then choosing a random sign will actually save you another factor of 2. And what you need to do, you actually need, if you want to run this algorithm with the 1 norm instead of the 2 norm, you need this to be epsilon squared concentrated, because then you'll get that this is epsilon. Sorry?
You can use Cauchy Schwarz.
Yeah. Yes, exactly. OK. So the kind of simple observation is that shifting from minimizing from the 2 norm to the 1 norm gives you this strong agnostic property. And what you'll need if you want to minimize with respect to the 1 norm is just a little bit more concentration in order to get all of this to work. Now, then the next question is, what's the complexity of expectation of min p of degree d, y minus p of x? And the complexity, it turns out that this can be written as an LP with order n to the d variables and order n to the d constraints. Okay, so just like in the low degree algorithm, you paid exponentially in d. Here you're also going to pay exponentially in d, and then you're going to have to run an LP solver to do this minimization. Whereas the algorithm from LMN was very, very simple. It just involved random sampling. So already you can see that the complexity of the algorithm involved to do this sort of minimization when you get rid of the 2 norm, because you lose Parsifal's equation, goes up dramatically. Okay, but it still runs in polynomial time. And then, and this is sort of the more interesting question, what happens if you want to find, you're given query access to a function f, and so in order to do agnostic learning, you can do the same proof, but it suffices to do this minimization, expectation of the absolute value of f minus p, where p is sparse. This is more complicated. Because you still want to run in time polynomial in n and 1 over epsilon and t, but it's not clear now that you should just take the, strangely, it's not clear that you should just take the largest coefficients. We believe it's not true that you should take the largest coefficients. I mean, you will get something like 8 or 4 times opt plus epsilon, but if you really want opt plus epsilon, I don't think you can just run the KM algorithm, but I don't have a proof that you can't. Okay. So what I want to tell you about is the complexity of this problem. So approximately, so you've fixed an arbitrary Boolean function, and you want to approximately minimize this quantity. Is it clear on what kind of quantity we want to approximately minimize? Okay. So a couple of observations here. One, the set of all p such that the 1 norm of p is bounded by t is convex. Okay, so the underlying set that you're optimizing over is convex. That's good. And also, the Cauchy-Levitz-Mansour algorithm, the sparse algorithm, sort of returns polynomials from within this convex set. So I have some polytope here, and I'm trying to minimize this particular quantity. Another good thing I know is that, think of t as being polynomial in n. If I were to expand out this minimization as a linear program, there would be 2 to the n variables and 2 to the n constraints. So if I were to try and solve it explicitly, it would take too much time. But I know the diameter of this convex set is at most t. And I'm trying to minimize some particular function here. Furthermore, when I run the KM algorithm, it's as we said, it outputs a hypothesis that is a sparse polynomial. So it's going to output some particular point here in the convex set. And then sort of what we could hope to do is implicitly approximate the gradient and do some sort of projected gradient descent within the polytope, within the convex set. So the hope is that you could implicitly solve this minimization problem using the KM algorithm and oracle access to F as some way to kind of locally see where you are in the convex set and kind of move in the opposite direction of the gradient, do gradient descent. And if you get outside of the convex set, then kind of implicitly project back into the convex set. It turns out you can do this. And this is what we did with Parikshit Gopalan and Adam Kalai. But I'm not going to talk much about it because I think it would take up too much time. But I'll just say that it can be done.
And your projection is using the KM algorithm?
Yes. Well, actually, it will take. So basically, you use KM to estimate the gradient. Mm-hmm. Then you walk in that in the opposite direction. And then after you've made this step, you may now be outside of the convex set. And there's a simple way to project back into the convex set. And then you'll use KM to estimate the gradient again and repeat. And the fact that it converges critically uses the fact that the diameter of the convex set is not too large. So there were two subsequent works, one by Kalai and Kanade, Varun, who's here, and one by Vitaly Feldman. And they both gave simpler proofs of this result using boosting. And actually, I should say they use something called agnostic boosting. And they're very nice, and there's a very cool, these agnostic boosting algorithms have some very, very cool properties. So what I wanted to do, because it allows me to kind of give a digression, I mean, no mini course on learning can go without mentioning boosting. So it allows me to kind of give a small digression onto boosting, and then talk about the sort of agnostic boosting that they do, and kind of at a very high level explain to you why you can use this to minimize this problem. Okay, so just as with the low degree algorithm, when you made this a 1, the algorithm became more complicated. You have to use linear programming. When you make this, when you minimize with respect to the 1 norm here, the algorithm again, at least even the simplified versions, are still, in my opinion, quite a bit more complicated than the Cauchy-Levitz-Mansour algorithm. So in the 5 minutes I have left, I wanted to quickly define a boosting algorithm, and then when we start tomorrow, I'll show you a boosting algorithm that you haven't seen before, most likely. It's very, very slick, and it has a self-contained analysis, so you'll totally understand how to do boosting in the standard setting, and then I'll be able to describe how to do boosting in the agnostic setting. Okay, so we're working, let's say, back in the pack model. So there's a concept C in C that labeling all of our examples, there's no noise. And we'll say that A is a weak learner. This is weak learner for C if for every distribution D, given access to random draws from D, A outputs a hypothesis H such that probability when x is chosen from D that h of x, let's fix an unknown concept, little c, that h of x does, I should say, let's say, equals c of x is at least 1/2 plus gamma. Okay, so in the typical pack scenario, you want your hypothesis to be, you want this to be 1 minus epsilon. Let's imagine instead that you have some primitive known as a weak learner that instead only gets you 1/2 plus gamma. So imagine it's correct only 51% of the time, but it works for all distributions D. And a boosting algorithm takes an algorithm A that's a weak learner, and it produces an algorithm A prime that's a strong learner. So it's a reduction that uses this weak learner as a subroutine and can use that to output a hypothesis that really is 1 minus epsilon accurate. And at a very high level, so you can imagine drawing a set of random examples. And so here are your random examples, and you would like to find a hypothesis H that is 1 minus epsilon accurate. And instead, so they're drawn from some distribution D. Let's call it D1. So you have these points labeled. I don't know, you output a hypothesis that gets, say, these points correct and these points incorrect. And then what a typical boosting algorithm will do is form a new distribution D2, and it will put more weight, so it will increase weight on these points that were incorrectly labeled by your hypothesis, and it will decrease the weight on these points that were labeled correctly by your hypothesis. And that will correspond to a new distribution D2. And then it will run the weak learner with respect to this. So with respect to D1, it had this original hypothesis. It'll run the weak learner again, simulating this new distribution. And that will force it to output a weakly accurate hypothesis. And because we increased the weight on the points that we were wrong, that will force this weak learner to kind of do better on these points that the original hypothesis was wrong. And we'll continue this process, and you have to do it in a somewhat clever way. And then, as you can imagine, if you take a weighted majority of all of these weak learners that you've output, you can prove. So Rob Shapiro was the first to prove that doing this type of thing will result in a strongly accurate hypothesis. And it also turns out that, I should just mention, that I'm not too concerned with how these algorithms that I've been describing right now perform in practice, but boosting has been a real success story and is used in practice all the time. You can imagine running some kind of heuristic that gets you kind of 53% accurate on your data set, and then trying to apply some boosting algorithm and rerunning the heuristic, and that's what people do, and it works extremely well. So next time, what I'll do is I'll show you how this works using an algorithm that you probably haven't seen before. And then we'll move to the agnostic boosting scenario, and I'll describe how you can use that to solve this minimization problem. And then we'll move on to we'll move on to some convex geometry. That's it. Thanks.